All right now we're going to work on the ground state electron configuration of silver. So we're now going to be engaging in that D block. We've avoided that so far by stopping all our electron configurations at calcium or earlier. But now we're going to work on that D block. Okay, so let's review. First we have what's coded in yellow on my periodic table is the S block, and that's groups 1 and 2. Don't forget that helium also counts in that S block area because he only has 2 electrons. So his position for electron configuration is actually over here. So make sure you've color coded your chart correctly with the S's of group 1 and 2 and helium, and that your P block is group 13 through 18, and that includes all the elements in those families, and those are in the P block. And now we get to the new guide for today. The D block at the dip, those are those transition metals where their oxidation numbers are going to be changing. And we call it the D block at the dip because this whole chart is shifted down so that you can actually picture it there. D block at the dip, it's at that shifted area. What we haven't talked about before is the actual rows are physically shifted. So scandium, titanium, all the way through copper and zinc, this whole D block area here looks like it's 4D because it's in the 4th shell or the 4th period or the 4th row or the 4th energy level or the 4th quantum number. There's actually a lot of words. They don't mean exactly the same thing, but there's a lot of words you could use to describe this row on the periodic table. But this is not the 4D row. This row is actually supposed to be up here in line with magnesium and all the way through to aluminum. Okay? The whole table is actually shifted down because the 3D row takes more energy to fill. So it's put it in its proper energy order, or its off-ball order, if you want to know the name of the rule. So when we do these, make sure you have 3D written right here. Okay? And then yttrium would not be on the 5D level, he'd be on 4D. So same thing, just remember you're taking one number off of that D block. All right, let's do the actual example. Silver, so I gotta find silver. Here he is, number 47, capital A, lowercase g. He's not silicon, so go carefully. And he has 47 electrons in its ground state because he's balanced with his protons. There's 47 electrons, 47 protons, because he's balanced, or he's neutral right now. And that's what we're looking at with the ground state. So just jot that down each time so that gets in your brain, and it's also good to have for your double check at the end. Okay, I hope you started to see the pattern that we're having here, because you always start with hydrogen. So the first one is going to be 1s2. And for every element except hydrogen, helium, or except hydrogen, you would be writing 1s2 to start. And then 2s2, 2p6. And go back over the next row, 3s2, 3p6, 4s2, not 4D, 3D, 3D10. And now people want to then say that this guy is 3p6. But remember, that's what we've already used that for aluminum's row. So this is still goes back to the rule 4p6. So you just have that little jump in there. 4s2, 3d10, 4p6. Okay. And the next row, 5s2, and 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 4d9. Okay. And if we were to write down or add up all these superscripts, each one is referring to its own unique electron. So if we summed up all of the superscripts, we would get the number 47, and that's our check that we have all the proper information on there.